Hi everybody, I'm the greatest living inventor, and today we are doing my invention, fractal uncertainty. So I'll write it down. Fractal uncertainty. Okay, so I'll take off my jacket. Okay, so a fractal matrix, I'll turn off the air conditioning because it's too hot. Okay, so the longer name of the invention is fractal matrix and computational uncertainty principle. I will explain, it will be apparent when I will explain. In 2017, two physicists, Zohar Ringel and Dmitry Kovirgin, published an article. Quantized gravitational responses, the sign problem, and quantum complexity. Okay, so this is by Zohar Ringel and Dmitry so it's without the I. Dmitry Kovirgin. It's not that what they are saying is true, but this was my starting point for this invention. So I'm giving you the history. Okay, so it's from 2017. And the article is called Quantized Gravitational Responses the sign problem and quantum complexity. Okay, so this is the name of the article, and here is a popular science summary in Cosmos magazine. Cosmos magazine. Physicists find we are not living in in a computer simulation. physicists okay, these guys find we are not living in a computer simulation. Okay, so so this is the article, and this is the popular short version. Okay, the article proves, quote unquote, we do not live in some matrix. Okay, you've seen the movie Matrix, I'm sure. The matrix. Well, if you haven't, go now, leave this lecture and go and watch it, because okay, the article proves, so-called proves, we do not live in some matrix, because they found something that will be difficult for the matrix to calculate. What I'm writing here started as my refutation, okay, like rebuttal, like I'm against what they are saying. My refutation to this article, but grew up to be a new and original twist on an old theory, on the old theory of simulation hypothesis. Okay, so the matrix is actually called in science simulation hypothesis. Okay, so so I have a new twist on this. Plus an explanation to Heisenberg's uncertainty principle that until now was unexplained. Okay, so the second thing is I don't have room, so I'll write it, I'll erase something. Okay, so the second thing is an explanation to Heisenberg's uncertainty principle. Okay, so I'm erasing these two. Okay, so so a new twist on the simulation hypothesis plus an explanation to Heisenberg uncertainty principle. that until now was unexplained. Okay, so now we are talking about Heisenberg uncertainty principle. Heisenberg proved that even theoretically with infinitely accurate tools, we can never measure both the location and the momentum, for our purpose, speed, of a particle. Okay, if there is some particle, okay, this is a particle. Okay, it's very, very small, and it's moving. Okay, so we can never measure both the location to know exactly where it is and also the speed, okay? The momentum, but I'm translating to simpler terms. The complete list of paired properties that Niels Bohr considered can be found in Wikipedia under complementarity physics. Okay, so if you look at in Wikipedia, complementarity, or let's write it on the side because after this I want to compare it to a computer, to a personal computer. Okay, so one pair is a location, exact location, and a momentum, or how fast it goes together with its mass. Okay, so if you look in complementarity in Wikipedia, complementarity, okay, it means things that are complementing each other. Like there is one and it's not the whole picture, we need also the other one. So together, but in this context, in complementarity in physics, it means we don't know both of them together. We know either this one exactly or that one exactly, but we cannot know both of them exactly. Okay? So position and momentum. Okay, I'm giving you all sorts of pairs that Niels Bohr gave us. Niels Bohr is written this way. Niels Bohr. Okay, also like Heisenberg, one of the fathers of quantum physics, quantum mechanics. Okay, so position and momentum is one pair, energy and duration is another pair, spin on different axes axis in many axes. Wave. And particle. Related. Properties. Another one. Value of a field and its change. At a certain position. And entanglement and coherence. Okay, so I'm shortening this a little because I want the other half of the board. Okay, and okay, so now it's shorter, less clear, but you've seen it. You can return in the video back if you need to. Okay, so and if you want to understand them, although it's very hard, you can see in Wikipedia in complementarity physics. Okay. Physics in Wikipedia. Okay, so this was the uncertainty principle, all of this. You cannot know this exactly and this exactly in the same time. You cannot know this exactly and this exactly in the same time. You cannot this and this exactly in the same time, okay, and so on. Like spin on the x-axis and spin on the y-axis at the same time, and so on. With the spin, we don't mean the spin is not like if something is rotating like this and and another axis is like this, it needs to be a different axis. Okay, if the object is rotating in diagonal like that, okay, so it's both on this axis and that axis, but now the axis is actually like this paper. Okay, it's like in diagonal, so this is the axis. So it doesn't count that you have a combined axis. It means one plane and another different plane, an orthogonal plane. Okay, at the same time. Okay, so okay, a different spin, like if it's spinning like this and also spinning like that. I don't know if you noticed, like I'm rolling the magic marker. Okay, so so now we're going on. Why the no matrix article is wrong? Why the no matrix article is wrong? Okay, why is the no matrix article wrong? The article claims that if we live in a simulated reality that runs on a conventional computer, not a quantum computer, let's say by aliens, and if we inside this reality will build a quantum computer, then the aliens computer will not be able to calculate the calculations of our quantum computer. The article says that although we have tried for years to simulate quantic processes on conventional computer, we failed. And this is because one of two reasons. Either we lack the analytic sophistication, or okay, we are too dumb, or this is there is a physical barrier to do this. It cannot be done. We are not dumb. The article says that creating a barrier in a conventional computer is not well defined. So they will create a barrier in a computer that operates in the quantum Monte Carlo method, which involves some mathematical problem with the sign. Okay, if you remember, that was the title of the article. Something with the sign. Of course, the sign problem. Of course, we can solve this immediately. Now I'm saying this. Of course, we can solve this immediately in saying that the aliens also use quantum computer or something better that we don't know. Even if we unreasonably assume that we invented the quantum computer before the aliens, the moment they see what that we invented it, it will overload their conventional computer CPU, and in a very short time the aliens will build a quantum computer of their own and copy us there without us feeling anything. Okay, they copy us to the other computer. This is also mentioned at the end of the article in Cosmos magazine. There is a caveat to this conclusion. Okay, I'm quoting. There is a caveat to this conclusion. If our universe is a simulation, there is no reason that the laws of physics should apply outside it. In the words of Zohar Ringel, one of the authors of the paper, the lead of the original paper, the lead author of the paper, he's saying, quote, who knows what are the computing capabilities of whatever simulates us? Okay, end quote. But if we stick with the assumption that the aliens use a conventional computer, okay, now again I'm saying this, but if we stick with the assumption that the aliens use a conventional computer, we reach something a lot more exciting. First of all, we don't need to go to the quantum world to find something that we cannot compute. The vast majority of equations in the real world are non-linear equations. Okay? Non-linear equations. Okay, we don't need to go to the quantum realm to find something that we cannot compute. The vast majority of equations in the real world, not the one in the classroom, are non-linear equations. And almost all of them we cannot solve. A classic example is the three-body problem, like Moon, Earth, and Sun. For example, the three-body problem. Okay, like Moon, Earth, and Sun, that Poincaré first tried to solve. That Poincaré first tried to solve, and we still cannot solve it accurately today. This was the first time in history that humanity ran into chaos theory. I'm sorry, it's everything like in points and I'm not elaborating. I can elaborate. I just don't want to this lecture to go over an hour. Okay, now we are at 28 minutes. I'll drink a little. Okay. Sorry. Calculating the gravitation between two bodies and how they rotate around each other in space, we can do accurately since Newton. But if you add another body to the system and it turns chaotic, the system is now chaos, and we cannot accurately calculate this. Okay, chaos is not like a mess. In mathematics, chaos is something very defined, which is what Poincaré found in the three-body problem, the chaos theory. Okay. And we cannot accurately calculate this. But we can numerically compute to a close approximation for a specific point in space what will be the effect there. And this also with great effort. In the article, okay, in the original article that I told you about, also largely, I'm sorry, in the article they also largely rely on a process which, when you add one more particle to the system, the number of possibilities grows exponentially. That process is based on the Hall effect, or Hall effect. Okay, so I'm not erasing this on purpose because I want later to compare. Okay, so in the paper, okay, this is the wrong paper that I told you about. They talk about the Hall effect. A quantum version of the Hall effect. That process is based on the Hall effect. But although there is a wonderful explanation about ordinary Hall effect in 60 symbols, and a nice interview about the quantum Hall effect in Stephen Griffin, I'm not sure they're talking about the quantum Hall effect or the, I guess they are comparing between the ordinary Hall effect and the quantum Hall effect, and I'm giving you in the video description links to both of them, but we don't care much about the Hall effect. We take another process instead. Okay, it's important that it will be a process that it's hard for the computer to calculate. Okay, so and a nice interview about the quantum Hall effect by Stephen Griffin. We will not go into the Hall effect because we will think instead about chaos in general and fractals like the Mandelbrot set in particular. Okay, so we will talk about instead, we will talk about chaos and especially about fractals and especially about the Mandelbrot set. Okay, so we're not talking about the Hall effect, although it's very interesting and you can see the videos. So in particular, we'll talk about this. By the way, what is created in the three-body problem is a Newton fractal. By the way, the thing that is created in the three-body problem, okay, like Earth, Moon, and Sun, is a Newton fractal that you can see in Wikipedia, and a prettier version in the book Chaos, Making a New Science by James Blake, called The Complex Boundaries of Newton's Method in the Color Pictures section. Okay, I'll see if I can find it quickly. No, I have it somewhere around the house, but I don't know where. So, so you can see it in this book. Okay, it's a wonderful book, but I cannot show it to you now. Okay, so I'm just writing the name of the book. Chaos, Making a New Science. By James Blake. Okay. And in the book it's called The Complex Boundaries of Newton's Method, and it's in the section with the color pictures. Okay. So if the problem is a chaotic system, it makes sense to try a solution that helps in another chaotic system, fractals, in computer graphics. If we look at a picture of a fractal that we created in our computer, for example, Mandelbrot set, okay, you should, if you don't know this, look at it in Wikipedia, it's beautiful. Okay? All fractals are beautiful, but this is like the mother of all fractals. If we look at a picture of a fractal that we created in our computer, for example, Mandelbrot set, there is an infinite amount of details. And the deeper you go, the more details we see. Let's see the time, 36 minutes. Okay, and we have... Okay, we need to hurry up a little. Okay, so there is an infinite amount of details, and the deeper you go, the more details we see. Does that mean that we need an infinite computer to draw this fractal from a bird's eye view, okay, from the top view? The picture that you see in Wikipedia when you open? No, we just need the right formula. For the Mandelbrot set, it's the equation f of z equals z to the power of 2, z cubed, sorry, z squared plus c. Okay? The formula is not important, I just want you to see that it's short. Okay? Okay, don't be scared by the formula, it's just to show you that it's a short formula that makes all these wonderful details. Equals z to the power of 2 plus c. Okay, some constant. All the endless, it's not the speed of light, it's just some constant. Okay, all the endless beauty of all the Zoom movies are inside this short and elegant formula. Even if you don't like math, you understand it's a short formula. And even if you don't know much about computers, you understand that the fact that it's drawn every day on personal computers means that you don't need infinite computing power. So, for example, if the above articles authors build a quantum computer that calculates something equivalent to building Koch snowflake, This is another fractal, Koch snowflake. I'm not drawing it because we need to hurry. Okay, it's also pretty, but we need to hurry. You can look in Wikipedia. So if, for example, if the above article's authors build a quantum computer that calculates something equivalent to building Koch snowflake, some fractal, this looks like it should take forever to draw. But since we only have to draw it up to the current limited resolution, the alien's conventional computer, in parentheses, or even a human personal computer, close parentheses, can draw it easily. Okay, Koch snowflake is like you have each time you have a line. You have a line and you take off the middle of the line. You cut it into 3 sections and you build another like a Sharpie point here. Okay, and you erase this side. And then you have like the Star of David. Okay, so in the first stage you have this, and after this you have each one of them has a sharp point of his own. And so on and so forth. Okay, and after this, in the next stage, each one has on them more sharp edges, and more, and it's like you need infinite time to draw it properly. But what I'm saying is that the screen resolution, when we draw something on the computer screen, the computer has just so many pixels. You cannot go infinitely detailed. So, and also our eye has finite accuracy, like we cannot see infinite detail with our eyes. Okay, never mind the computer. This is why like going from 4K to 8K is ridiculous. Okay, and beyond this is even more ridiculous. Okay, so in TV screens. So, so in the same way, the alien's computer doesn't need to draw this infinitely accurate, just accurate enough for us. And if we come closer, then it shows us just the section that we are looking at. We cannot see from up close all the landscape. Okay, so we just need this sector. So it's like zooming in the computer. It's the same physically, because we cannot stand here up close and see everything that's going on. If we look down, then it shows us only this part. It calculates only this part, and so on. Okay. So then, the alien's conventional computer, or even human personal computer, can draw it easily. And if they want to zoom, enlarge, into a deeper and deeper specific part, that the conventional computer only has to work on a small, then that conventional computer only has to work on a smaller and smaller part of the picture, and can easily do it. Okay, now the next part, reality built from fractals. Okay, so here I'm showing you a picture from what's called the Mars demo by Tim Clark. Okay, Mars by Tim Clark. Okay, it's a DOS demo, A demo is like a demonstration of graphics and sound. Here it's very small, so it doesn't have sound, and it's from 1993. And back then it was amazing. Today it's like only very nice. Okay, so this tiny, so I'm just showing you the picture. You can look in Wikipedia, I'll give you the link. This is a frozen picture from this demo, but you can, okay, in the real demo you can go through this with your mouse, and moving the mouse you can travel forward, backward, left and right inside this landscape. Okay, and this landscape is made with fractals. Okay, so it's fractal landscape. Okay, this tiny amazing demo by Tim Clark is only 6 kilobytes. Okay, 6 kilobytes. Of course, you can travel inside the demo for an hour, okay, and see more and more details they don't repeat themselves. Okay, about half the size of this text page that you are reading now. Okay, and runs perfectly smooth on an old 486 computer. Okay, my old first PC was 486, and yet generates a whole interactive Martian planet surface based on a fractal. By the way, I was the one who uploaded it first to poet.net website. My nickname there was Chompy. Okay, so if you look in, if you want to see the demo, you can go to poet.net, which is a website for demos and the demo scene, and my nickname there was Chompy. And you can look in, you can find this demo and you can see that the person who uploaded it was Chompy. That's me in the nickname. Okay, so my theory is that aliens, okay, now we're back to the aliens. The aliens draw our reality exactly like fractals. And all our physical laws of nature that we found are only a rough approximation to the elegant equations that unfortunately we don't know of the aliens. Our knowledge is in this metaphor is like the Feigenbaum constants. Okay, Feigenbaum constants. Let's write it instead of all this. Okay, so Feigenbaum constants one of the constants is the ratio between the circles of the Mandelbrot set. Okay, if the Mandelbrot set looks like something like this, okay, it's like something like this, then the ratio between this and this, okay, or here. Maybe it's here. To be honest, I don't know, but there is some ratio in the Mandelbrot set which is close to 4.669. 4.669 and something. Okay, it doesn't repeat itself. It's like like an infinite number. Irrational number, sorry. So this falls into the category of we lack the analytic sophistication. Remember I said one of the possibilities that they said in the original article that maybe we are too dumb. Okay, so this is this example, this case. So this falls into the category of we lack the analytical sophistication that the article authors have considered. The proof I found to the fact that we are indeed inside the conventional computer, not infinitely powerful, comes from Heisenberg's uncertainty principle in quantum mechanics. Okay, so we are back to this. Okay, so now we are getting to the invention after a lot of background. Okay, 51 minutes, we need to do the invention in a hurry. Okay, so our rules of nature are like a rough approximation, like this Feigenbaum constants. Okay, so uncertainty, standard explanation versus fractal explanation. Standard explanation, bottom-up calculation. Okay, so now uncertainty. Standard explanation okay versus fractal explanation. Okay, this is my explanation. This is the science conventional explanation. Okay, so the fractal explanation is top-down. The standard, let's start with the standard explanation. The standard explanation is the bottom-up calculation. Bottom-up calculation. And my explanation is top-down calculation. Okay, so different approaches. Okay, so the effect in standard explanation, bottom-up explanation, the effect comes from the wave nature of the particle. You can read it in wave-particle duality in Wikipedia. I'll give you all the links in the description of the video. Okay, wave-particle duality. In the fractal explanation, the top-down calculation, now when I was a teenager, when Tim Clark created his amazing Mars demo, the personal computer graphics card was limited, for example, by two parameters, number of colors and screen resolution. Okay, so I'm erasing this. Now we are talking about this. You know what, if I will write everything, I will not have time. I will just explain it verbally. Okay, I'm sorry. No, I'll write it down. Okay, so now we are talking about fractal uncertainty. Okay? fractal, just fractal. Okay, the fractal explanation. Okay, so this is all based on my experience as a lowly programmer, a graphics programmer in the era of DOS. Okay, so when I was a teenager, when Tim Clark created his amazing Mars demo, the personal computer graphics card was limited, for example, by two parameters: number of colors and screen resolution. We could use the limited memory of the graphics card VGA either for more colors and less resolution, or for more resolution and less colors. Okay, so let's call it VGA graphics card. Okay, it has limited memory. We can do either more colors and less resolution, or more resolution and less colors. Okay, so colors and resolution. We could use the limited memory of the graphics card VGA either for more colors and less resolution, or for more resolution and less colors. We cannot do this perfectly and this perfectly. We cannot do this perfectly and this perfectly. Can you see the similarity? Okay, it's like an equivalence from this to this. There was a trade-off, barter trade or compromise, between horizontal resolution and number of colors. Okay, there was also a trade-off between vertical resolution and screen refresh rate. How many times in a second the screen is redrawn. Okay, vertical resolution versus screen refresh rate. So again, things that we cannot have together. We can have either this perfectly and this lousy, or this perfectly and that lousy. Okay, we cannot have both of them perfectly. Let's say it's the same thing in our reality. Then, if we know exactly the position of the particle, resolution, we know less about its speed, the ratio between screen refresh and its progress between the pixels. Okay, so if we know that the resolution very good, we don't know the screen refresh rate very good, so we don't know the speed. Let's say it's the same thing in our reality. Then if we know exactly the position of the particle, resolution, we know less about its speed, the ratio between the screen refresh and its progress between the pixels. The next pair is energy and time. You cannot know, okay, this is like the position and the momentum, the speed. It's not exactly speed with mass. Let's say it's the same, the next pair is the energy and time. Okay, energy and time. You cannot know exactly how much energy a particle has and also when exactly it left the system. See Einstein's box. Okay, I don't have time to write everything. We're over an hour now. We have to finish. If you think of color as energy, it's the same way that red light rays have lower frequency and so also lower energy. Then blue-purple light rays, red light has less energy than violet light, than blue light, blue-purple light rays. And if we think of screen refresh rate as time, then there is a trade-off correlation between these two properties because of the link between horizontal resolution and vertical resolution. Okay, because these two are related, then these two also are related and there is a trade-off. Because here there is a trade-off and here there is a trade-off and these are related. Okay, so you see it's like energy and duration. What about the property pair of spin in different directions? Okay, this. This is similar to something in VGA graphics called Mode X, invented by the legendary programmer Michael Abrash. Okay, Michael Abrash. Okay, if you remember the original Quake 1 in DOS, it has a lot of use in Mode X. Okay, Mode X lets you unfold the folded memory of the VGA card and treat it as a planar memory. Then you can define a few pages of memory of the screen either to the sides or up and down and flip between them for smooth animation. If we treat these ways of unfolding as the frames of rotation, let's say we divide the memory into 4 horizontal spread pages and in each one the object is rotated a quarter of the rotation in a certain direction, let's say horizontal rotation. Of course, we cannot use it in the same time for rotation around another axis in another speed, I mean. Let's say vertical rotation. Okay, PS, when I found out that there is a book called Programming the Universe, a Quantum Computer Scientist Takes on the Cosmos by Professor Seth Lloyd, who calls himself a quantum mechanic, I was worried that I'm just reinventing the wheel here, repeating what someone else already thought about. But I read the section about the Heisenberg uncertainty principle, and the explanation is not similar to mine. As far as I can understand, his book talks about the universe running a quantum computer, not conventional. Okay, so that's it. I hope I didn't overflow and that it was clear, and this was my invention. I'll see you in my next invention. Thank you very much. Thank you.